We're going to start with some simple transformations, the vertical shifts and the horizontal shifts. Your vertical shifts and your horizontal shifts basically preserve the shape of the graph. In the case of vertical shifts, they just shift the graph up or down by the same number of units, by a fixed number. In this case, we have two graphs here. We have y equals x squared, and we have y equals x squared minus 5. The y equals x squared is actually your top graph, your one that is purple looking graph. The y equals x squared minus 5 is the green graph on the bottom. So these two graphs have the exact same shape. The only difference is they are shifted. The green graph is shifted down. If we plug in the x values, notice your x values on each graph are the same. And we look at the corresponding y values, notice that the difference between the two y values have a delta y of negative 5 each time. So this is a constant shift downward, and that negative 5 corresponds to the negative 5 out here on this function y equals x squared minus 5. Similarly, if I look at horizontal shifts may be a little bit easier to see. These are shift left and right. Again, they preserve the shape of the graph. This orange table has the graph y equals x squared, which corresponds to the purple graph in here. And this greenish table has the graph y equals x plus 3 quantity squared. Notice this graph is just on the right, the green one is just shifted to the left 3 spots. Notice the y values are all the same in this case. But if you look at the x values differ, and they differ by, the corresponding x values differ by a constant of negative 3. So in this case, delta x is negative 3 for all of these values. Notice the difference between the horizontal shift, the 3 was inside when I squared it, versus the vertical shift, the 5 was on the outside of the function. How do vertical and horizontal shifts work? Well, basically, if you have a function f of x, you obtain the graph f of x plus c is basically the graph of f of x shifted upward c units. The graph f of x minus c is the graph of f of x shifted downward c units. If I have f of the quantity x minus c, just shifts to the right c units, and f of the quantity x plus c shifts to the left c units. Notice when it's on the outside it shifts up and down. When it's on the inside it shifts left and right. On the outside it behaves the same. Plus goes up, minus goes down. On the inside it does the opposite. Minus goes to the right, positive goes to the left. Now we can do multiple transformations at one time. If we have y equals the quantity x minus 1 squared minus 4, this is the basic y equals x squared graph. It's shifted 1 unit to the right, the minus inside goes the opposite, and 4 units down. So if I start out with my basic graph, y equals x squared, y equals the quantity x minus 1 squared shifts to the right 1 unit, and y equals the quantity x minus 1 squared minus 4 shifts to the right 1 unit and down 4 units. Notice the shape of all these graphs are basically the same. All I'm doing is transforming them, shifting them left and right. Find an equation that shifts the graph of f of x equals x squared plus 2x plus 3 left 4 units and up 5 units. We know 4 is on the inside of the function left and right. 5 is on the outside of the function. So if I want to look at shifting this function would be y equals f of the quantity x plus 4. Inside the function is left and right, and then the plus 5 is on the outside of the function. So if I look at this y equals f of x plus 4 plus 5, the x plus 4 part becomes x plus 4 squared plus 2 times x plus 4 plus 3, and the 5's on the outside of just plus 5. Now if I want to simplify this, this becomes x plus 2 squared plus 2 times x plus 4 plus 8. Let's talk about vertical and horizontal stretching. If we let c be a positive number and we pick x comma y lies on the graph of f of x, then if I multiply my function f of x by c, if y equals c times f of x, this is a vertical shrinking or stretching, and the point x comma cy lies on this graph. It should make sense that the x is not affected by anything you plug in, and the c only affects the y value. Now, if I put the c on the inside, y equals f of c of x, f of c times x, this is a horizontal stretching or shrinking, and the point x over c comma y lies on this graph. Let's see how this works. If I have y equals c times f of x, we know the c out front is the vertical amount. It's on the outside of the function. So if c is greater than 1, this is a stretching vertically. If c is between 0 and 1, this is a vertical shrinking. If c is on the inside of the function, f of c of x, if c is greater than 1, this is a shrinking, and if c is between 0 and 1, this is a stretching. Again, inside the function behaves opposite of what you would imagine. Let's look at an example. Here's my original function f of x. Nice little V formation, okay? If I want to look at y equals 2 times f of x, the 2's on the outside. Outside the function affects the vertical amount. And since it's greater than 2, it stretches it. So it affects the y value. Remember our rule back here? We said c times f of x, then the point x times c of y lies on the graph. So if we go back here, my c in this case is 2. It affects the y values. So if I look at my points, I have these points, negative 2, 4, 2, 4, and 0, 0. The 2 is going to affect all the y values. So I'm going to have the point negative 2, comma 2 times 4, 0, 2 times 0, 2, 2 times 4. Again, notice this 2 is constant on each one of these. And that 2 comes from the way we defined our function of y equals 2 times f of x. So I have the point negative 2, 8, 0, 0, and 2, 8. And if I plot these points, this is what my graph looks like. Notice this stretches the graph vertically. Similarly, if I put a number inside of my function f of 1/3 x, this is the number that's going to affect it. Again, inside the function is going to affect it horizontally. Now, inside the function also only affects the x values, not the y values. That's where this 1/3 comes from. And remember, it affects it in the opposite way. Remember the point x over c, or x divided by c. So my c in this case is 1/3. So again, I have the points negative 2, 4, 0, 0, and 2, 4. So I'm going to take each of these x values, and I'm going to divide it by a third. So negative 2 divided by a third, comma 2. So when I divide by a fraction, I flip and multiply by the reciprocal. So negative 2 times 3 is negative 6. So I have the point negative 6, 2. 0 divided by a third is still 0. And this should be the point 0 here, sorry. And then 2 divided by a third, comma 2. Well, 2 divided by a third is simply 6, so 6, 2. So I have 3 points now, negative 6, 2, 0, 0, and 6, 2. Notice when I plot this graph, all I've really done is take the original graph and I've stretched it. In this case, I've stretched it by a factor of 3, which is the inverse of this 1/3. Alright, reflections of graphs. If I have a negative on the outside, the graph of y equals negative f of x is a reflection of the graph y equals f of x across the x-axis. I'm flipping the graph up and down. Whereas if I have a negative inside the function, y equals f of negative x, this is a reflection of the graph y equals f of x across the y-axis. Let's see how this works. Let's say this is my original function, y equals f of x. If I have a negative f of x, all I do is start at the x-axis and I flip it up and down. So notice the x-intercepts are 1 and 4 on the original graph. Notice the x-intercepts on the new graph are 1 and 4. All I've done is flip this graph upside down across the x-axis. Similarly, if I start with y equals f of x, the purple graph again, and take f of negative x, it flips it across the y-axis. So in this case, the original graph had a y-intercept of 0, 4. The new graph has a y-intercept of 0, 4. Notice how it's just a mirror image of itself. Let's combine transformations. We have this graph y equals negative 4 times x minus 5 squared plus 2. This is just a parabola y equals x squared. The negative reflects it across the y-axis, across the x-axis. The 4 stretches it by a factor of 4. The x minus 5 shifts it to the left 5 units, and the plus 2 shifts it up 2 units. So according to the rules of PEMDAS, we should do the transformations in this order. We go inside the function. We start with the number in front of the x. That number and that negative sign, if there is any, this horizontally stretches and shrinks and flips things. The minus 5 shifts it left and right. The negative 4 out front shrinks it or stretches it vertically and flips it. And finally the plus 2 shifts it up and down. So in this case, we do not do any stretching or shrinking or flipping x with the x value. We go to the left 5, we shift to the right 5, not to the left, I apologize. The right 5 units. We flip the graph, we stretch it by a factor of 4, and then we shift up 2 units. Let's look at an example of this. Describe how the graph of this equation y equals negative radical x minus 5 plus 2 can be obtained by transforming the graph of y equals the square root of x. We go inside here first. We're going to shift the graph to the right 5 units. We're going to reflect across the x-axis because of the negative out front. And we're going to shift the graph up 2 units based on this formula.